Dear friends, good morning. My name is Pankaj Dumka. I am working as an assistant professor in JP University of Engineering and Technology. So today's topic will be work and heat transfer. So you all must be knowing that work and heat transfer, they are basically the ways in which the system interacts with its surrounding. Now, discussing first the work transfer. What is work transfer? If this is my system, so when I'll say that this system is interacting with its surrounding in terms of work transfer. So before going into that, let us discuss how we define work in mechanics. We say that the system is doing work when some amount of force is acting in the direction of displacement, or when a force is acting in the direction of displacement, we say that the work is done in terms of mechanics. But how to relate this mechanics work with your thermodynamic work? So here is the catch. In thermodynamics, a system is said to be doing work, or a system is doing work, or we say that the system is doing work when the sole effect on things which are external to the system can be reduced to the raising of weights. So if system is producing this type of effect of raising of weight, then we can say that the system is doing some work. Now, it is not always necessary that system physically raising some weight, but the essence should be such that we can feel that the system is raising weight. How? Let us see. Let us say that this is a motor which is driving a fan, and this is my control volume. So how to perceive this effect? If I remove this fan and insert a pulley, attach a thread to it, wound the thread around it, and suspend a weight W. If I consider my system as motor, now the moment I start this motor, this weight will start rising up. So in this sense, I can say that this system of mine is doing some work on its surrounding by raising weights. Now, in thermodynamics, if some amount of work is done on system, then we say that this is negative. And if some amount of work is done by system, then we say that it is positive. So this is my sign convention, that if the system is doing work, then we will always consider it positive, and if some amount of work is done on system, then we will say that is negative. The unit of work is joule. Now, how many types of works are there? How you categorize them? So first one is PDV work. Let us say that I have a piston cylinder device like this. At any instant in this piston, the pressure is P and the volume is V. And I have lot many weights attached. So this gas which is at pressure P is balancing the weight, the total weight of these small components plus the atmospheric pressure, weight force because of atmospheric pressure. So this is balancing this. If this area of piston is A, so this gas from inside is balancing this external load. If I remove this small weight, so this is the original position, now the piston acquires this position. after removal of few of the weights. What I did, and the weight which I have removed is very small, and the situation which I am showing you is exaggerated to a huge extent, magnified to a large extent. Let us say that this has moved at distance dz in vertical direction, and a slight amount of pressure imbalance has been created. A negligible amount of pressure imbalance is created, because of which this piston has moved in this direction. So the force which causes this piston to move will be P into A, area of this. And as this piston has moved by this distance, so this force, when coupled in the displacement in the direction of force, will give you the amount of work done by this gas onto its atmosphere, if this gas is my system. So this is what? This is the change in volume during the process. So if this is my initial position, and let us say when I have removed every weight from here, this is my final position. So the total amount of work done by this gas system from moving 1 to 2 will be this PdV, and this is called as non-dissipative displacement work, or PdV work. Why non-dissipative? Because I am assuming no friction to be existing here. No friction, nothing. If at all it exists, so the motion of this piston is so slow that it can be neglected very well. This is my PdV work, or displacement work. And as the piston moves, because of the imbalance, small imbalance created, it is always in an equilibrium state, like this. It has moved from 1 to 2. I know every state passed, so I can join it. So here I can integrate this very well. Now friends, why I have written this differential work as dW and d with a cut? Why? Because this work is a path function. That means this depends on the path followed by system. What path the system is following. For example, let us say this is 1 to 2, one path A. Another path, this is B. So PdV work is what work? PdV work is basically the area under a curve in PV plot. This. So if this is my path A and this is my path B, so obviously the area under 1V2, that is W1 to 2 along path B, will be more than W1 to 2 along path A. But my end states are same. So what can I conclude from here? I can conclude that the work is depending on the path chosen by system to arrive at that particular state. So this is a path function. Hence, this is designated like this. That simply means if I want to integrate it between these 2 points, I cannot write it like this. No, this is wrong. Why? Because the work is that form of energy which cannot be stored by a system. It only comes into picture when system interacts with its surrounding. That's why the name energy in transition is coming into play. Now the second type of work is shaft work. Let us say that I have a fluid in a container, and this container, let us say, is adiabatically sealed. Now what I am doing is I am inserting a paddle wheel in this system, in this fluid, and I am stirring it. So what I am doing basically, I am imparting this much amount of energy per unit time onto this fluid. And what is happening, because of the friction available here, this energy will be getting stored in the fluid if this is adiabatically sealed. So this stirrer is doing work on the system only when the friction is coming into play, because if there would have been no friction, so this stirrer will be doing no work. So hence this is a dissipative work. Now the third type of work is known as flow work. And to know flow work, let us consider this case, that we have a layer of fluid at section 1 at pressure P, and it has displaced to this point, that is dx distance. If this layer has want to move from this point to this point, then it has to displace this amount of fluid, that is, if cross section area is A into dx amount of fluid has to be displaced by this layer to make its way through. So the amount of work which this layer is doing onto its neighboring layer to make its way through will be equal to the force which this layer is exerting multiplied by the distance moved. This work is normally given in terms of mass of fluid element displaced. So this can be written as PA dx upon this dm is density into this volume. And what is the volume? It is A dx. So hence P by rho is the displacement volume. Flow work. And in thermodynamics, we do not talk of this term often, we talk of specific volume. So this is what we know as flow work. This is also known as flow energy. Why? Because it is also known as pressure energy, because this small layer is doing work on its adjoining layer, on its nearby element, just by the virtue of the pressure at which this layer is. That's why this is also known as pressure energy. So whenever we have an open system like this is section 1, this is section 2. So some amount of fluid has to move in and some amount of fluid has to move out. So when this fluid element is pushed in, so this layer is doing some work on this element, and when this element is pushed out, so some of the layer which is here, this will be pushing this element. So flow work will coming into picture in this case, that is in open system. This is an important concept. Now friends, let us discuss few of the quasi-static process works. Let us discuss the first one. If the process is isochoric means volume is constant. So that process can be drawn on PV plot like this. 1 to 2, up or down depends. So if I am interested in work interaction, so I will try to find out this work in this fashion. But as the volume is not changing, so this will be 0, this is 0. So in case of isochoric process, the closed system performs 0 work. And mind it, integral PdV is only for a closed system. So this is the case. Or in other sense, if I try to find out the area under this will be a point. So area will be 0. Again, the work transfer will be 0. Now come to second case, isobaric process, where the pressure remains constant. P is constant. So this is my pressure axis, this is my volume. So let us say this is my pressure. The volume has increased from V1 to V2. So if I am interested in calculating the amount of work, so W1 to 2, that will be dV from 1 to 2. As pressure is constant, it will come out, so integral of dV will be V2 minus V1. So this is the work interaction in case of isobaric process. Now friends, let us discuss the third process. Say a system is performing, PV is a constant, a rectangular hyperbola type of process, this from state 1 to state 2. And now I am interested in knowing what is the area under it. So work done is in this process will be 1 to 2 p dv. So replacing this p by c by a v, so c integral 1 to 2 dv by v. So this will give me c natural log v2 by v1. What is c? C is p1 v1, at the same time it is p2 v2. So I can write this as p1 v1 natural log v2 by v1, or p2 v2 natural log v2 by v1. But I also know from this that v2 by v1 is p1 by p2. So this will be same as ln p1 by p2. Now if the system is doing some polytropic process, that is pv to the power n, which is a constant. So what is the amount of work interaction in this? This is that pressure volume plane, and this is that pv to the power n from state 1 to state 2. So work interaction in this process will be 1 to 2 p dv. What is p? It is constant upon v to the power n. So this will be c integral 1 to 2 v to the power minus n dv. So on integration we will get v2 to the power minus n plus 1 minus v1 to the power minus n plus 1 divided by minus n plus 1. So this constant means p1 v1 to the power n will be equal to p2 v2 to the power n, and this will be a constant. So when I multiply this constant by v2, I'll use this. When I multiply this thing by v1, I'll use this. So I will get p2 v2 into v2 to the power minus n plus 1 minus p1 v1 into v1 to the power minus n plus 1 whole thing divided by minus n plus 1. So this will be p2 v2 minus p1 v1 divided by minus n plus 1, or p1 v1 minus p2 v2 divided by n minus 1. So this is my general polytropic process work interaction. Friends, in few of the competitive examination, I have seen that this type of problem has been asked. They used to say that if you have a process pv to the power n is a constant, then they say what will happen when n is 1, when n is 2, when n is 0, when n is 1.4, when n is infinity. What type of process this is? So when I say that n is equal to 1, so pv will be a constant. So I say it is pv is a constant type of process. And if they say that, let us say that the system which you are using is a gas, and that to a perfect gas, so PV is a constant, means for a perfect gas we know PV is equal to mRT. If PV is constant, mass is constant for that particular gas, R is characteristic gas constant for that, so T will be a constant. So this will be a isothermal process. If n is equal to 0 means PV to the power 0 is a constant, so this will be P is a constant, so this will be a isobaric process. And if this n is a constant, so for this we have to solve it further. Let us say PV to the power n is a constant. You take PV to the power n whole to the power 1 by n is C to the power 1 by n, another constant C prime. So this will become PV 1 by n into V is a constant, some another constant. So if I keep this n as infinity, so that will give me p to the power 0 v is a constant. That simply means if n is equal to infinity, the process is v is a constant. That means it is a isochoric process. That's it. So in this way, you can tell which process is which. And now how to plot it. If this is my starting point, expansion is taking place, this is n is equal to 0, isobaric process. This is n is equal to infinity, isochoric process. This is n is equal to 1, isothermal process. And on increasing n is equal to 1.4, n is equal to 2. And this is adiabatic process. Now let us discuss a very interesting case, that is free expansion. What is free expansion? When a gas has to expand against a vacuum, that is known as free expansion. This is a gas, here a vacuum is there, this is my piston, and it is expanding like this. So people initially thought that let us try to find out what is the work done by this gas against this vacuum. So they said this is my initial condition. The moment I remove this partition, this is not my piston, this is my partition. I remove this partition, the whole gas will occupy this volume. So they say this is pressure, this is my initial point, this is my final point. But the problem is the gas rushes so quickly to occupy this vacuum that we won't be able to locate the path. So this is my initial one, this is my final, so this is a sort of irreversible process. So we cannot find integral PdV with the help of this. So later on they said, let us do this. Let us remove this one partition and place several partitions like this. And remove one partition, you will get equilibrium condition. Remove second, remove third in this, and mind it, this is adiabatically sealed. So they said this. Okay, initial state, removed one, find like this. They got the different states, they joined it, and they got a path, and they have started finding out the work interaction. But friends, what is happening? You are doing some work against a vacuum. So vacuum does not offer any resistance. So if it does not offer any resistance, that simply means you are doing no work, because the work is always done by a system against an external resistance. If the surrounding is not offering any resistance to us, so then how can we find the work interaction? There will be zero work interaction. So if initially this is my system, I try to find out the work done, I got this, where it is very difficult to find PdV. Then I remove this single partition with so many number of partitions. Again, this is my gas, and I got this. This is correct, but I cannot find this. I can find this PdV in this case, but this will come out to be zero as the vacuum is offering no resistance. So what is the work interaction in case of flow work? Work interaction in case of not flow work, free expansion, it is zero. Now, before I end this lecture, I would like to give you a brief note on heat transfer. Now, what is a heat transfer? Heat is that type of energy which comes into picture whenever there is a temperature difference. Temperature difference is the driving potential for heat to flow. If there is a temperature difference, then heat will flow. There are three modes of heat transfer: conduction, convection, and radiation. Now there is a sign convention which we people used to follow, is that if system is gaining heat, if there is a heat transfer to the system, then that will be considered positive. And if the system is losing heat, that means there is a heat loss from the system, then we will consider it negative. Like work, heat is also a path function. Like work, heat is also a path function. That's why it is also called as energy in transit. One more thing to be remembered in this case of heat, that all the energy interactions except those which are occurring because of temperature difference, all energy interactions are called as work interaction. So what is heat interaction? Heat interaction is that interaction of energy where the energy interacting with its energy system is interacting with its surrounding by the virtue of temperature difference. So temperature difference is the sole cause of heat. Mind it, this is very important. Now there is one more thing you should remember, that what is specific heat? Specific heat is the amount of heat required to raise a unit mass of a substance by unit degrees. That means if you have 1 kilogram of a substance, so let us say 1 kilogram, and then the amount of heat required to raise this 1 kilogram of substance by 1 degree Celsius, say, will be the specific heat of this particular thing. So what is specific heat? It is the amount of heat required to raise the unit mass of a substance by unit degrees, that is specific heat. This is having a unit of kilojoule per kilogram Kelvin or joule per kilogram Kelvin or degree Celsius, depends. The specific heat for solids and liquids does not depend on process, but for gases it depends on process. If that process qualifies as a constant pressure process, then that will be designated by Cp, and if that is constant volume, then that will be designated by Cv. Now friends, there is one more thing, sensible heat and latent heat. A system is said to be doing a sensible heat, or the system is interacting with the surrounding in terms of sensible heat interaction when there is a temperature change in the system. So if there is a temperature change, then we will say that the system is interacting with its surrounding in terms of sensible heat. For example, let us say water. If I am increasing the temperature of water from 10 degrees Celsius to 100 degrees Celsius, then what I will say, 10 degrees Celsius, 100, that the system has gained heat, and we can sense it by the incremental temperature. So sensible, the energy which can be sensed. And the other one is known as latent heat. So that heat, that is the amount of heat, or that is that particular energy in the form of heat which comes into picture whenever there is a phase change. So if I am supplying some heat to my system and the phase of that system has converted from liquid to solid or solid to liquid, then the amount of heat interaction here involved in this particular case will be called as latent heat of fusion. When the system has changed from liquid state to vapor state or from vapor state to liquid state, then the amount of heat energy interaction involved here is known as latent heat of vaporization when liquid to vapor, and the same thing, latent heat of condensation when vapor to liquid. And when the system is converting when the system is changing its phase directly from solid to vapor, then we will say that the latent heat, or from vapor to solid, then we will say that the latent heat of sublimation is coming into picture. Before I end this lecture, I would like to give you I would like to tell you something about this latent heat. Friends, whenever you talk of latent heat of vaporization, that latent heat of vaporization is very sensitive to pressure, and later on I will tell you this. If this is my volume, this is my pressure, I plot a vapor dome for water, let us say. This is my first pressure, this is my second pressure. They are very close, but still the latent heat interaction in this case is more in comparison to this. That is, latent interaction in 1 is more than 2. So whenever there is a phase change from liquid to vapor or vapor to liquid, the latent heat interaction is very sensitive towards pressure, whereas from liquid to solid and solid to liquid, this is not the case. Thank you so much. Hope that you have understood whatever I have taught you people today. If you liked my video, then please